This is Unit 6, Introduction to Exponential Functions. We'll be covering Lessons 11 and 12, Exponential Situations and Interpreting Exponential Functions. Start with the bridge, turn to page 230, pause the video, work through these two questions, then come back and compare your answers. Question number 1 says the area A of circle C is given as a function of the radius based on the rule A equals pi r squared. What is the area of C circle given radius 5 inches? Alright, so we're going to use this function A equal pi times 5, which is the radius. We're going to replace that with r in this equation, squared. Alright, so go ahead and multiply 5 times 5, or use your calculator to get 25. So the area equals 25 pi. That's the exact area. Now if you put in 3.14 or an approximation for pi, you're going to have a number that's rounded off. So if it asks for the exact value, you're going to put 25 pi. And that's going to be inches. Okay, did that tell us what we're measuring in? Yes, inches squared. All right, so for B, we're going to replace r squared. Replace r with 12. So this is going to be 12 squared times pi. 12 times 12 is 144 pi. That's your answer. So area equals 144 pi. All right, now one thing that I'm forgetting to do, I do not want you to forget to do, is put your units squared. Okay, what we're measuring in. And then put that square up here. Now volume is in 2 dimensions, actually 3 dimensions. Okay, area is 2 dimensions, volume is 3 dimensions. All right, so the formula is volume equals 4/3 pi r cubed. What is the volume of a sphere if I give you the radius of 5 inches? All right, so we're going to take 4/3 and use your calculator or use Desmos. 4/3 times pi times the radius cubed. Okay, 5 times 5 times 5. 5 times 5 is 25. Times 5 is 225. Times 4 is 500. So it's 500 over 3 pi inches squared. Okay, 5 cubed is 125. 125 times 4 is 500. That's how we get 500 over 3 pi inches cubed. All right, this time we're going to put in 12 for the radius. All right, this time we're going to replace the radius with 12 inches. So we're going to take 12 and we're going to cube it, putting it in for r. Okay, and then 4/3 pi times 12 cubed. All right, on your calculator, put in 12 to the 3rd power. 12 to the 3rd power is 1,728. Let's go ahead and move that pi to the end. We're not going to put in pi and let the calculator round it off. We're just going to include that in our answer. So that goes at the end. Okay, so 1,728, which is 12 cubed. We're going to multiply that times 4 over 3. And then simplify. Put 1,728 over 1. All right, 1,728 divided by 3 is 576. Okay, so that's what we're left with on the top. Multiply that by 4. 576 times 4 is 2,304. Okay, so that's going to be pi and it's written as 2,304 pi inches cubed. All right, turn to page 231. Let's complete the warm-up. So pause the video, try to answer these two questions on your own, and then come back and compare. All right, we have a graph here of the accumulated rainfall in Las Vegas, Nevada in the first 60 days of 2017. We're going to use this graph to support your answer to the following questions. So let's look at what the x-axis represents. Remember, x is our input, and our input is always going to be time. So our x-axis is showing day of the year in 2017. And then our output is going to be an amount. On our y-axis, we have the amount of rainfall in inches. Is the accumulated amount of rainfall a function of time? So let's think back to where we started learning about function notation. The answer is yes, because for each number of days, a certain amount of rain fell up to that time. So there's one particular value for the accumulated rain at any point in time. All right, remember, y is always the output, x is always the input. So is the rainfall a function of time? So the answer is yes. Is time a function of rainfall? No. Okay, time is not a function of accumulated rainfall. There was no rainfall in the first 10 days. This means that for the amount of rainfall, 0 inches for the input of 0, there are lots of times that could be the output. So with a function, for every input, you have only one output. But just remember that y is a function of x. All right, so rainfall is a function of days of the year. Let's turn to page 232 and complete the activity, moldy bread. Claire noticed mold on the last slice of bread in a plastic bag. The area covered by the mold was about 1 square millimeter. She left the bread alone to see how the mold would grow. The next day, the area covered by the mold had doubled, and it had doubled again by the day after that. All right, now I've underlined things as I was reading through it, but you should do a 3-read. Read it first, get the idea of what the problem is saying, and then read it again, highlight numerical data, make sure that you understand what that is, assign any variables if needed, and let's work on answering the questions. Now, if the doubling pattern continues, how many square millimeters would the mold cover 4 days after she noticed the mold? Okay, it's going to be 16 square millimeters, or 2, okay, times 2 times 2 times 2, or 2 to the 4th. We start with 1. Let's write that equation out. So y equals 1, the initial amount, times our growth factor. We're doubling it, so our growth factor is 2. Okay, raised to the power of x, or t. I'm going to use t for time. Okay, and we want to know what happens after 4 days. So that's why we replace the t with 4. 2 to the 4th is 16. Represent the relationship between the area in square millimeters covered by the mold and the number of days since the mold was spotted using a table of values. Okay, so we're going to start this table on day 1. We have 1 square millimeter. We double it on day 2. We have 2. We're going to double it again. 2 times 2 is 4. Double it again. 4 times 2 is 8. Double it again. 8 times 2 is 16. And then one more time, double that. 16 times 2 is 32. Now if we graph that, you can see 0, 1, 1, 2, 2, 4, 3, 8, 4, 16, 5, 32, and you can keep going. It's going to increase rapidly and it's going to curve and go up. So this is showing growth. Here's our equation. We start with 1. We wrote it up here. I'm going to write it down here as well. Our initial amount times the growth factor raised to the power of x, or t. In this case we used d because it told us to use d for time. Time is always going to be our x. Discuss with your partner the relationship between the area covered by mold and the number of days of function. Oh, I'm sorry. Let me start over again. Discuss with your partner to answer this question. Is the relationship between the area covered by mold and the number of days a function? If so, write blank is a function of blank. If not, explain why it's not. So remember, I said y. Let me write it with text. Okay, y is a function of x. Okay, we usually write it like this. F of x equals some amount. Okay, we usually have an expression, an equation that you insert x into to find your total amount. So y, f of x can be called y. Y is always a function of the input x. All right, the area covered by mold, the output is a function of time. Y is a function of x. Okay, at any given time since the mold was spotted, there's a certain area of the bread that is covered in mold. The number of days that have passed are a function of the area covered by the mold up to a certain point. For example, when the entire bread is already completely covered, we stop measuring. The area of mold would correspond to more than 1 day. So we don't have a way to write this relationship using an equation, but you could write a table to reason it out. What we're saying here, trying not to confuse you, but your bread can be completely covered by mold, and then we stop measuring. All right, so again, what is a function of what? Is x a function of y, or is y a function of x? All right, just remember to always start with y. So we're going to say that y is a function of x. Now the independent variable, independent is always going to be your input, so the independent is x. And the dependent variable, once we input x, we get an answer. Our output is going to be our dependent variable. It depends on what x is. All right, when making the equation, note this. So write this down in your workbook. A times b to the x. A is the starting amount, b is the growth or decay factor, and x is the exponent, which is time. X is always time. When b is more than 1, it's growing. When b is a fraction or less than 1 and greater than 0, it's going down. It's showing decay. All right, on pages 233 and 234, we have activity 2, functionally speaking. Here are some situations we have seen previously. For each situation, write a sentence in the form of blank is a function of blank. Indicate which is the independent and which is the dependent. Independent is going to be your y. Independent is going to be your x, and dependent is your y. Then write an equation that represents the situation using function notation. In a biology lab, a population of 50 bacteria reproduce by splitting. Okay, so we're going to have it. We're going to half it. Let me write that down so you'll understand what I'm saying. We're going to half it. Okay, they split. Here's the bacteria. It splits into 2. Okay, so we're going to end up with 2 more. Okay, we saw this on the board. We saw it in the book. So are we halving it? Yes, but we're actually doubling it. Okay, so we start with 1 and we double each of those. That for one cell, we split it in half, so we get 2. Then we're going to split these 2 in half, and we're going to end up with 2 times 2, or 4. Okay, well, let's see how to write that. The number of bacteria, the output, your y, is always going to be a function of your input, or time. So y is a function of x. The output is the number of bacteria, and our time is hours. The independent is our x, and our dependent is our y. Okay, so let's write this in an equation, or a function. So f of t, you can also call that y, is equal to the initial amount, 50. Our growth factor is 2 to the t. All right, question number 2. Every year after a new car is purchased, it loses 1/3 of its value. Let's say that the new car cost $18,000. Now your growth factor is not 1/3. That's how much we're losing. Our growth factor is how much is left, how much remains. So take 1 and subtract 1/3. 1 in terms of thirds is 3/3. 3/3 minus 1/3 is 2/3. So 2/3 is what remains. Okay, we start with $18,000. Okay, the value of the car is a function of the number of years since it was purchased. The independent variable is the number of years, the input, always going to be time, and the dependent is going to be the value of the car. So f of t equals the initial amount times, remember, not what we're losing, but what's remaining. So it's going to be 2/3 to the t. In order to control an algae bloom in a lake, scientists introduced some treatment products. The day they began treatment, the area covered by the algae is 240 square yards. Each day since the treatment began, 1/3 of the previous day's area remains covered by the algae. Time is measured in days. So the area is going to be a function of the number of days. Output is always a function of input. The independent variable, independent is going to be your x. Independent is always going to be time. So the number of days since treatment is your independent variable. The dependent variable is going to be the area in square yards. So we write that function f of t equals the initial amount, 240, times, and this time we've got to read it carefully. It said 1/3 remains. Not 1/3 is taken away, but 1/3 remains. So 1/3 raised to the power of t. All right, go through the lesson debrief in your workbook, highlight important information. Complete this sentence for this situation. All right, remember, output. So our y is always a function of our x. So let's go here to this problem. Okay, so the output is going to be, the input is going to be time. So that's going to be hours. And our output is bacteria population. So the amount of bacteria is our output. It's a function of the amount of hours. How is P related to the function f given by f of t equals 1000 times 2 to the t? All right, P is our population, so we got to go up here to find out what P is. All right, what do you think? Write it down. The population is related to the function f because the number of hours the population is doubling. How are these equations like or different from the equations you've written previously without function notation? One of the things that I notice is that we're replacing y with function notation. Is there anything else that you notice? So y is the same as f of x, g of x. That's our y value, our output. How are the exponential functions here like or different from linear functions we saw earlier in the course? So you can think about that and add to that if you want. Go through the summary and glossary. You need to know what an exponential function is, know what that definition is, and how to write that equation, especially the decay function. The growth factor or the decay factor is going to be the amount that's remaining, not what we take away. Okay, look at these graphs, look at the tables, know how to graph in Desmos, and interpret what that means in context to the problem. All right, do the cool down. Beaver population 6.11. We have a graph showing the population of beavers in a forest. So the output is going to be the number of beavers and the input is going to be time in years. Explain in your own words why we can think of the beaver population as a function of time in years. Because the number of beavers depends on the time in years. In any given year, there's a particular number of beavers in the forest. There's not two different amounts. There's only one amount for each input x. What is the meaning of the point label Q? We've got Q up here. Point Q indicates that 3.5 years after 1995, the population was about 550. Now write an equation using function notation to represent the situation. So we start at 50. Okay, we're doubling it each time, 50 to 100. Look at the y values. Doubling it again to 200. Then this should be, in year 3, 400. And then in year 4, 800. Okay, so 50 times 2 to the t, where t is the years after 1995, and p of t, or the output, or y, is the beaver population at that time. All right, turn to page 242 and complete the warm-up. Lynn and Diego are discussing two expressions, x squared and 2 to the x. Lynn says, I think the two expressions are equivalent. Diego says, I think the two expressions are only equal for some values of x. Do you agree with either of them? Explain or show your reasoning. So stop right here and think about it. Okay, the best thing what I would suggest to do, if you don't know what to do at all, is to make a table. Or if you don't know where to start, make a table of X and Y values. Okay, so we've got Lynn and Diego. Okay, so we're going to start with 0, 1, 2, and so forth. Okay, so for Lynn, we're going to take our values and we're going to square them. 0 squared is 0, 1 squared, 1 times 1 is 1, and 2 squared is 4. We're going to use those same numbers, or you can pick different numbers, it doesn't matter. I'm just going to choose 0, 1, and 2 because I want that 0. I want the initial value. Okay, I'm going to raise that to the X. Alright, so I'm going to take 2 and I'm going to raise it to the 0 power. 2 to the 0 is 1. Anything to the 0 power is 1. Okay, then I'm going to take 2 to the first power. Okay, so that's going to be 2. And then 2 to the second power is going to be 2 times 2, or 2 squared, which is 4. Okay, so let's look at those amounts. We can go, let's see, even one more. 3 times 3 is 9, and 3 squared is 9, and then 2 to the third power is 8. Okay, if we find the value of x squared and 2 to the x for different values of x, say 0, 1, 2, 3, and 4, we can see that they are not always equal. Okay, I probably didn't go high enough. So here's a table comparing x squared to 2 to the x. Okay, they're not always equal. They're sometimes equal. Okay, we can see that here in 2 squared. But they're not equal when x is 3. 3 squared is 9, and 2 to the third power is 8. Okay, they're equal when x is 4, but not when x is 5. The higher that x gets, the quicker that exponential number gets larger than the squared term. All right, let's complete activity number 1, the cost of solar cells. All right, we have the cost in dollars to install solar panels that produce 1 watt of solar power. Okay, that's a function of the number of years since 1977. Okay, so we start here in 1977. It's labeled on the x-axis. Okay, so if we go out 1 year, that's 1978, 1979, 1980, 1981, and so forth. So we're going to add the number on the x-axis to 1977. Okay, what is the statement f of 9 is approximately 6 saying about this situation? So I'm going to go, this is the input, this is our x, so I'm going to go out to x is 9, and that's approximately 6, because we're counting by 5s, 5, 10, 15, 20. It's a little bit above 5. What that says is 9 years after 1977, go ahead and add 9 to 1977, that's in 1986, the cost in dollars for 1 watt of solar energy was about $6. What is f of 4? Okay, so 4 years after 1977, the cost of 1 watt of solar energy was about $25. Okay, and f of 3.5, here's 3.5, that's approximately 30. Not exactly. Now those values represent the cost in dollars of 1 watt of solar energy. In 1981, that's 4 years after 1977, and halfway through 1980, or 3.5 years after 1977. So we're looking closely at that graph, talking about it different ways. All right, when the function f of t equals 45, so this time we're looking at f of t, we're looking at the output. So we're going to go up here to halfway, but this is 40, 50, this is 45, and go down, and our x is 2. So what is t? What is our t value? In other words, what is the time? Okay, that represents 2 years after 1977. In 1979, the cost in dollars of 1 watt of solar energy was $45. Okay, right here. Page 243. By what factor did the cost of solar cells change each year? If you get stuck, create a table. All right, so I'm going to take 2 points. I'm going to start with that initial point, 0, 80. Now you find another point, any other point. Okay, now if I can, I'm just going to go out 1 and go up. That's 1, and it looks like 60. Let's find our change in our y values. In other words, what is 80 minus 60? 80 minus 60 is 20. And then 0 minus 1 is 1. We're going up by 1. Okay, so solar cells that doesn't look right. All right, let's make a table. And I'm going to start with 0, 80. It's a little bit fuzzy here on the slide, so look in your book, page 243. Okay, now let's find another value. Okay, this is 160. Okay, this is 240, let's see, 45, 50, 55, 60, 245. All right, we can stop right there. All right, now we're going up by 1 in the x direction, so I can simply take my y and divide it by my x. 60 divided by 80, we start with that second number, divide it by that first y. Okay, we can take off a pair of zeros, we're dividing by 10, and then you can divide both of those by 2. Divide 6 by 2 and 8 by 2. 6 divided by 2 is 3, 8 divided by 2 is 4. Okay, or you can write it as a decimal, 0.75. Okay, that's how the solar cells are changing. Okay, we have left, we start with 80. The next year we have 3/4 of that left. Each year we go up, we still have 3/4 left, so we're taking away 1/4. Now how would you interpret this statement if f of -1 equals 100? Do you think this statement is reliable? Okay, in 1976 it cost $100 to install solar panels that produced 1 watt of power. This might not be reliable because we only know what the exponential model holds from 1977 to 1987. Outside of that time frame, this model may not apply. We may not have had solar panels in 1976. We just don't know. So when we go into that negative, when we input a negative time value, it's not always reliable because we can't go backward. All right, page 243, we're going to talk about paper folding. The thickness in millimeters, we're going to call that T, of a folded sheet of paper after it's folded n times is given by this function. T of n equals 0.05 times 2, because we're doubling. Every time we fold the sheet of paper over, we're doubling the thickness to the n. So n is going to be your x, or n is going to be time, your input. What does the number 0.5 represent? That's going to be the initial amount. The sheet of paper is 0.05 millimeters thick. Now use graphing technology, use Desmos, put this in your calculator. You can substitute y for t of n, or you can put t of n equals 0.05 times 2 to the n. If you're using function notation, this is fine, or you can also write it as y equal 0.05 and then times 2 to the x. Okay, and this is what it should look like. Okay, it's going to be a curve, an exponential curve. Now, how many folds does it take before the folded sheet of paper is more than 1 millimeter thick? Okay, this is the thickness. Okay, so we've gone up, we folded it once, twice, 3 times, 4 times. So 5 times it's more than 1 millimeter thick. After 4 folds, the paper is 0.8 of a millimeter, but at 5 folds, it's 1.6 millimeters. All right, the area of a sheet of paper is 93.5 square inches. Find the remaining visible area of the sheet of paper after it's folded in half once, twice, and 3 times. Okay, so you're going to use this equation. I didn't have it back on the other sheet, so let me write it here. All right, so y equal the initial amount, 93.5. Okay, how much is remaining each time? 1/2. So this is our growth factor. We're calling it decay because it's actually reducing each time we fold it, raised to the x. Okay, so if we substitute in 0 here, we're going to get 93.5. Substitute in 1, 1/2 of 93.5 is 46.75. Okay, replace this with 2. 1/2 squared is 1/4. Okay, 1/4 of that amount is here, 1/8 of that amount, and so forth. So now, how do we write that function? A equals the initial amount times 1/2 to the n. And then put that in Desmos, use graphing technology to graph that function. Check and see if it looks like this. And let me know if this slide has any mistakes in it. Anything that I've said that you don't understand, ask questions. The area of a sheet of paper is 93.5 square inches. In this context, can n take negative values? So what do you think? Can area be negative? N cannot be negative because area cannot be negative unless we can unfold the original sheet of paper. I don't think that that's possible. Can A take negative values? No, the area can never be negative. Area has to be positive. No matter how many times it's folded, we're not going to ever be negative. All right, go through the lesson debrief in your book. Highlight the vocabulary, go through the summary and glossary. Please reach out if you have any questions. Come to tutoring, ask questions, send an email, and I will get back to you with a response. I want to be able to help you get this done. Don't forget to do the cool down bacteria population. Now I want you to start doing this on your own. Okay? So complete this. If it's not in Canvas, at least find a place in your book to write it down, but it should be open and available in Canvas. And then complete the practice problems for this assignment. Complete them first in your workbook and then transfer your answers into Canvas.